Now that we have an understanding of what a standing wave is, we're going to sort of quantify some of the properties of standing waves and have a look at different scenarios. So you can see here strings and air columns open at both ends is where we're going to start. Now I'm going to try and develop this as we go sort of across the page and down the page. We're going to start out first of all with the fundamental frequency. Now the fundamental frequency is also known as the first harmonic. So that term, the first harmonic, will become important as we go through. Now, if we're dealing with a string, we're always going to deal with the string having the same length. So we're not going to change the length as we go down. So we'll keep the string length the same. So in these first diagrams, we're going to have strings. And so the envelope for the fundamental frequency basically looks like that. So that repeating pattern of node, antinode, node. So nodes at the end and an antinode in the middle. That'll represent like that. Now if we're looking at air columns, again we'll keep the length of the air column the same, and we'll develop these both in conjunction as we go, because basically they are the same sort of scenario, just slightly different representation because of the fact that these two lines here representing the tube or the pipe or that forms the air column itself. On the end of an air column we're going to have antinodes. So think of it as basically being the same as the string, just sort of shifted across a little bit, so that we then have antinodes at the end and a node in the middle, and so the shape that we get then looks like this instead. So you can sort of see that if we continue to extend this out this way, we'd get that same sort of shape. And so you can see there that both of those, the length of the air column is represented by half of the wavelength. So we'd need to extend that shape another antinode and node along, or in the case of an air column, a node and antinode along, to get one full wavelength. The next sound that we would hear is then going to be the second harmonic. Again, if we keep the length of the string the same, we're now going to have a node in the middle, so two nodes at the end and a node in the middle. That means that the shape we're going to get is going to look something like this, and so we would have, let's fix that bit up, we're then going to have two antinodes positioned between those nodes. Similarly for the air column open at both ends, we're still going to have an antinode at each end, and we're now going to have an antinode in the middle as well, and that means we're going to have nodes in between them. So the shape that we get there, again, would look like that, and in both cases the length is now going to be equal to the wavelength of the tone itself. If we then go up to the third harmonic, again take that one step further, we're now going to have two nodes in the middle with the nodes at the end, and again we'll have those antinodes in between them, so we'll have that shape being formed, and so you can see there then now that the length of the string is actually longer than the wavelength of the sound. And again, just the comparison to the air column open at both ends, we're now going to have an antinode, or two antinodes in the middle with nodes in between them, and hopefully you figured out with this one, we're now going to see that the wavelength is actually 3 halves, or 1.5 wavelengths. So I'm going to write that as L is equal to 3 lambda on 2. Now, you might not have noticed the pattern there straight away, but if I make this a little bit more obvious, I'm going to call that 1 half wavelength, 1 lambda on 2. Well, if we look at lambda, we could express that as being 2 half wavelengths, so 2 times lambda on 2, and we could express this as being 3 half wavelengths, or 3 lambda on 2. So hopefully now you can see that pattern a bit more clearly. In each case we've got this factor of lambda on 2, we've got 1, 2, and 3 as being the constants that are being multiplied out the front, and you'll notice that the 1 matches up with the first harmonic, 2 with the second harmonic, and 3 with the third harmonic. So if we look at the nth harmonic, so generalizing this now, the nth harmonic, the length is going to be given by n lambda on 2. So if we know what harmonic is being played on a string or an open-ended air column, and we know something about the frequency, we could then figure out the wavelength, and we can figure out the length of the air column. So we can link all those ideas together. So as I said, keep in mind here that you also can tie that back into the equation V equals F lambda. So if we know lambda here, we've got lambda here as well, so we can link those two equations together. Now, a different type of air column that we need to address as well is an air column closed at one end. Now, there's an aspect here about the way that the Queensland syllabus deals with this that I'm not a big fan of, because it's different to the way that you would see it in most other resources. We're going to start off with the fundamental frequency again. And in this case, I'm not going to... I'll mention the harmonics, but it's more about the mode of vibration. So this one we're going to call it the first mode of vibration. And that would also then be the first harmonic, but I'll come back to harmonics a little bit later. So in this case, again, we're going to keep the length the same, but as we've got in this situation, it's an air column that's closed at one end. That means we're always going to have a node at the closed end, and we're always going to have an antinode at the open end. So in this case, the shape of the wave is going to look like that. And if we wanted that repeating pattern of node, antinode, node, antinode, node to get one full wavelength, you can see in this case the length of that air column is lambda on 4. It's 1/4 of the wave. For the second mode of vibration, as I said, we'll come back to harmonics. For the second mode of vibration, we're still going to have, again, node at the closed end and an antinode at the open end, but we're now also going to introduce another node-antinode pair in the middle. So the shape that we're going to get there now looks something like this. And if you notice there, we've got node, antinode, node, antinode. We need to go one more to a node to get to the full wavelength. So the length of that air column is 3/4 of a wavelength, or 3 lambda on 4. If we go to the third mode, we'll see an extra node-antinode pair in the middle again. So still with an antinode at the end and a node at the fixed end. This one gets a bit tricky trying to get the spacing right. So we'd have a node, 2 more nodes there and 2 more antinodes. And again, that repeating pattern, that shape of the waveform being produced. And if you count up the number of quarter wavelengths, so node to antinode would be 1/4. So there's 1, 2, 3, 4, 5 of those. So the length there is 5 lambda on 4. Now this one's not quite as obvious to figure out. When we're looking at the generalization here, if we're looking for the nth mode of vibration, the equation is L is equal to 2n minus 1 multiplied by lambda on 4. So basically, if we go back and look at each of those, so when n is equal to 1, 2 times 1 is 2 minus 1 gives us 1, so we'd end up with 1/4 of a wavelength. In the second mode, 2 times n minus 1 is 3, and so we'd end up with 3/4 of a wavelength. For the third mode, 2 times 3 is 6, minus 1 gives us 5, so we'd end up with 5/4 of the wavelength. Now, if we look at the harmonic, I'm going to mention this because it's a relevant point to make. And I want to try and avoid confusion if you do happen to look up other sources of information. With the harmonics, think of it as basically being the number of repeating patterns of the fundamental shape. So if you look at the fundamental shape in this scenario, we're going from a node to an antinode, so it's that shape there. So there's one of those for the first harmonic. If we look at the second mode of vibration, we've got one of those positioned here. If you then sort of reverse it, we get a second one going from antinode to node, and then we get a third one going from node to antinode at the end. So this second mode of vibration is actually the third harmonic. And if we follow that same sort of pattern again, the third harmonic is actually, the third mode of vibration is actually the fifth harmonic. As I said, dealing with closed-ended air pipes, we're not going to worry about harmonics. The syllabus doesn't treat them in that same way. So you need to be aware that it's the mode of vibration that you're interested in, whether it's the first, second, or third. But if you do look at other resources and identify that it's first, third, or fifth harmonic, you need to make sure you're clear that they relate to the first, second, and third modes of vibration. Just one last point to make about the harmonics. So notice that there are no even harmonics. That's basically because if we tried to reproduce this shape, so this antinode-node pattern, if we went to a second one, we'd end up back at a node, but that doesn't work for a closed-ended air column. We need to have an antinode at the end. So you can't get even harmonics for a closed-ended air column. You can only get the odd harmonics. And again, make sure you're very clear on the fact that we're dealing with the mode of vibration, which relates to the length of the air column using this equation in the bottom right-hand corner here.